Hello everyone. In this lesson we're going to study ionization energy. And ionization energy is going to be related to atomic radius but also nuclear charge, so you might want to look back at your notes on that. And we'll look at the trends that it shows in a period and the trends that it shows in a group. So there is a quiz associated with this lesson, so be ready for that quiz. It should be coming up tomorrow. The aim is, what is ionization energy? Please copy down this do now on a separate piece of paper. You can title it with the same title as this lesson, and make sure you have today's date on it as well. So copy down this do now, separate piece of paper for classwork. And defining ionization energy. So ionization energy is defined as the amount of energy required to remove the most loosely bound electron from an atom. Okay. There's a little bit in that. So it's actually, ionization energy is an amount of energy, but it's not just any amount of energy, it's the amount of energy required to remove the most loosely bound electron from an atom. So in short, it's the amount of energy required to remove an electron from an atom. And it has a lot to do with the size of the atom, and it has to do with the amount of attraction that the nucleus has for its electrons, in addition to the size of the atom. So those are the things that I think the most that affect the ionization energy. And I do have to say, I think it helps to clarify that the larger the ionization energy, the more work the scientist is doing to get the electron loose. So since it's defined as the amount of energy required to remove an electron, then basically just think if it's harder to get the electron off, that's higher ionization energy. I'm not sure how each of you feels about using Table S. I can tell you Table S, in my opinion, is awkward and way too big, but I can tell you that if you didn't want to learn anything about ionization energy in this lesson, you could just know that you can look on Table S to get the ionization energy for every single element. I don't think it's the best way to learn about ionization energy, but just so you know, Table S does have the ionization energy of every element listed. Let's compare the ionization energies of these two atoms. So on the left we have an atom whose atomic number and nuclear charge is +3. So that is definitely lithium, in case you want to look on Table S. And we also have an atom who seems to have 8 electrons in its valence shell and has a nucleus with 10 protons. So that is definitely neon. So when we're deciding which of them has the higher ionization energy, there are two things I think that matter a great deal. Firstly, in the lithium atom, if you look at its electron, it is quite a long distance away, we'll call that R for radius, from its nucleus. And if you look at neon, these electrons are a shorter distance R away from the nucleus. This has to do with the number of orbitals that each of these atoms has. Each of them has 2 orbitals. But since these elements have the same number of orbitals, but very different nuclear charges, +3 and +10, then the one who has a larger nuclear charge and the same number of orbitals will have a smaller radius. So the radius and the nuclear charge are both going to matter here. I think that the radius part is probably the easier part to explain, so I'll start with that. Firstly, you can think of this as sort of like magnets in your refrigerator, or 2 magnets. You probably remember that the closer you hold 2 magnets together, the larger the force between them is, and the farther apart you hold 2 magnets, the smaller the force between them is. We can think of that the same way as the force of attraction between electrons and protons. So in this atom, where the electrons seem to be rather far from their nucleus, the distance r is larger, and therefore you can see that this is similar to two magnets that are far apart from each other. And two magnets that are far apart from each other have a low force of attraction. Therefore, if the force of attraction between electrons and these protons is small, then the ionization energy is low. And again, that low ionization energy is a result of the large radius of the atom. Now, if I look on the right-hand side over at the example of neon, the distance r between the nucleus and the electrons is a lot smaller. And just like two magnets that are being held together closely, the force between this electron and these protons is going to be larger because the atom is smaller. If the force of attraction between the electron and the nucleus is larger, the ionization energy will be larger. So I just went ahead and said that it would be high. All right, let's look at the effect of atomic radius and the effect of nuclear charge. So we're going to use table S to get some of this data. What I want you guys to do right now is pause the video and gather some data on radius, nuclear charge, and ionization energy for these two elements, beryllium and chlorine. And then I want you to gather some nuclear charge, radius, and ionization energy for helium and lithium. Yes, I know I switched these two. I did do that on purpose to make the comparison a bit easier. So I grabbed some data and put it in here. And I wanted to point out that the reason why I chose to compare beryllium and chlorine for this first example is because they have really similar atomic radii and different nuclear charges. So really similar atomic radii, I chose 99 and 100, but I also wanted to make sure that they have very different nuclear charges. And so in this way, we'll be able to really fairly assess the effect of nuclear charge on the ionization energy of the atom. And in the second example, I just wanted to consider atoms that have similar nuclear charge, but very different atomic radii. So the really similar things here are the nuclear charges, really, really similar, but the atomic radius is enormously different. So basically, what I think it's pretty obvious, but I'll just say it, is that you can really, really see how a larger nuclear charge is going to give you a larger ionization energy. So in effect, the more protons these atoms have, the more it can attract its electrons. And more attraction for electrons is going to make the ionization energy larger. That is, the amount of energy needed to remove an electron is a lot larger if you have more protons in the nucleus. On the other hand, remember, on purpose, I chose two atoms that have similar radii. So I wonder if that this high number of protons leading to a large IE, or a large ionization energy, I wonder if that would still hold true if the radii of the two atoms were very different. So you can use this table below it to help prove that one to you. So in this case, I decided to keep the nuclear charges fairly similar. Lithium does have a larger nuclear charge, but it's very similar to helium's. And the radii are really, really different. You might remember that the reason why you can get a larger radius with a larger nuclear charge, because that's sort of uncommon, the only way you can really do that is if you have different numbers of orbitals. So really, really quickly, helium only has one orbital. It has a nucleus, and in its first ring of electrons, it has 2 electrons. Whereas lithium actually has 2 entire orbitals. It has 2 electrons in the first ring and 1 electron in the second. So in any case, lithium is a lot larger, and that's what leads to its larger radius. But the point is, the larger the radius here, the lower the ionization energy, even though the nuclear charge is higher. So yeah, there are more protons and they are expressing an attraction for electrons, but if the radius is a lot larger, like this guy, then you can think of it like the case of the magnets. These magnets are farther apart from each other, and therefore it'll be easier to remove them. It'll be easier to pull them apart because they're already far apart and the force of attraction is low. Therefore, the ionization energy will be low. Now let's look at some trends across periods. I have chosen here elements all from the same period, and it goes lithium to neon. These are all period 2. And we need to grab a little bit of data on the nuclear charge and the atomic radius and the ionization energy. So use table S to grab that data now. I just had a sudden attack of laziness, so I only put in data for 3 of these elements. I have lithium with its nuclear charge, radius, and ionization energy, but I also have that data for carbon and neon, and that is enough to show the trend. Remember that there are 2 major factors at play. Not only is nuclear charge an important factor in determining ionization energies, but so is radius. Now this trend is just for the trends across a period, and what you need to remember across the period is that all the elements in a period have the same number of orbitals. Therefore, they are roughly on the same order of magnitude of size. So here's the way I would explain the data. Firstly, I would just say the nuclear charge for lithium is quite small, and therefore its radius is relatively large, at least compared to these other elements in the same period with the same number of orbitals. So the smaller nuclear charge, meaning the fewer the protons, the more the electrons get to spread out. See, electrons are attracted to protons, so the fewer protons you have, the more the electrons will leave the nucleus, the more they will spread out from the nucleus, and the radius will be larger as a result. That larger radius, meaning that the electrons are farther from the nucleus, is going to result in less attraction between the electrons in the nucleus, and that will also give you a lower ionization energy. So lower ionization energies match up with less attraction. So low ionization energy, less attraction, that's going to give you a large radius, and that's a result of small nuclear charge. And then if you go down to the bottom, where you have still lithium and neon have the same number of orbitals. They both have 2 orbitals, but neon has 10 protons rather than 3. Its considerably larger nuclear charge will make a considerably smaller atom. The nuclear charge it's going to attract those electrons and draw them in, so the atom will be a lot smaller, and as a result, the ionization energy will be much, much, much larger. It'll be much larger because there will be more attraction between electrons and protons when the size of the atom is small. So if I want to explain the trend in ionization energy across a period, I would just say that across a period, ionization energy increases because the nuclear charge increases while the number of orbitals stays the same. I do think this last bit here is one of the most important parts of this explanation, that the number of orbitals is staying the same, because we will find other examples throughout the periodic table where the nuclear charge increases, but the ionization energy decreases. So if you just say these 2 things, the blue and the red, I don't think that's enough, because you're leaving out all the examples where ionization energy decreases with an increase in nuclear charge. The only way this explanation is complete is if you make an oblique reference to the fact that you're only talking about elements that have the same number of orbitals. So if you're only talking about elements that have the same number of orbitals, then an increase in nuclear charge will result in an increase in ionization energy. But it's only true if those elements have the same number of orbitals. And I think we'll see some counterexamples in the next slide when we're looking at elements and their trends down a group. So I'll alert you to my laziness right now. Let's just grab some data for lithium and francium, and I will choose rubidium as my middle example. I'll get the nuclear charge, atomic radius, ionization energy. If you want something to do, you can look it up on table S. Alright, so I have chosen the alkali metals, also known as group 1. And let's see, nuclear charge of lithium is positive 3, its radius is 130, its ionization energy is 520. Now as I go down the group of group 1, and I get to rubidium, whose nuclear charge is plus 37, significantly larger, you can see that the radius is larger as well. Now, normally, if we're looking at elements within a period who have the same number of orbitals, a larger nuclear charge results in a smaller radius. But in this case, the larger nuclear charge has resulted in a larger radius. The reason, in short, is that rubidium has several more orbitals than lithium has. Lithium actually only has 2 orbitals, and sodium will have 3, potassium has 4 orbitals, rubidium has 5, cesium has 6, and francium has 7 orbitals. So the reason why the radius of rubidium is a lot larger than lithium's, it's not because it has a larger number of protons. More protons usually makes the atom smaller. The thing that's made rubidium so large is that rubidium has 5 orbitals, whereas lithium only has 2. Those extra orbitals are going to make the atom larger. And with the larger radius, you're going to get a lower ionization energy. In general, larger radii will give you low ionization energies. It's just like when you have the 2 magnets far apart, the force you would need to pull them apart is quite low. Let's make the example a little more extreme. Let's move on to francium, and we'll have 87 protons in the nucleus. And francium also has 7 orbitals. It's a lot of orbitals. And all of those 7 orbitals, despite the fact that it has a nuclear charge of 87, those 7 orbitals will give it an atomic radius of 242, which is quite large for something whose nuclear charge is so large. So this is a large atom, mostly because it has 7 orbitals, and that large radius is going to lead to an even smaller ionization energy than rubidium's. The smaller ionization energy is a result of the electrons and the protons being far apart because of this large radius, and the farther apart they are, the easier they are to remove each other. So when I explain the trend in ionization energy going down a group, I just say that more orbitals leads to a larger radius, which leads to a lower ionization energy. So nuclear charge increases and atomic radius decreases across a period. So across a period, that means elements that all have the same number of orbitals. So the nuclear charge is going up, yeah, and the atomic radius is going down, yes. So the nuclear charge increases and the atomic radius decreases as you go across a period. Why don't we see that pattern going down groups? It's because you're adding orbitals. We've reached the end of the lesson. Please copy down this pair up on a separate piece of paper that you've made for classwork. Just put it right under the do now. And also copy down this summary. You can just make a really rudimentary sketch of this periodic table. It doesn't need to be complex. And copy down this summary, and we'll work on that in class as well. And don't forget, there is a quiz associated with this lesson, so be prepared for a quiz when I see you.